So last lecture over the reactions of alkenes. So in this lecture we'll look at reactions that go through what are known as carbenes, and then we'll look at how alkenes can be used to make polymers. Okay, so if you take an alkene and this is your recipe, so you react it with CHBr3, or it could be CHCl3, and then with a base. So that's what's known as bromoform, and that's what's known as chloroform. Okay, so bromoform or chloroform with a strong base. So what happens is, first of all, because of the 3 bromines or the 3 chlorines, and that's a fairly acidic hydrogen, and so if you react it with a strong enough base, like potassium tert-butoxide, then this can do an acid-base reaction to begin with, where that can take off this hydrogen, and those electrons become a lone pair on carbon. So you make this carbanion, right, because carbon's got a negative charge, a lone pair of electrons, and that's not stable. So this particular one is not stable. And so what happens next is a bromine just leaves, takes the 2 electrons with it. So now you have a bromine attached to carbon, 2 bromines attached to carbon with a lone pair, and that is what's known as a carbene. Is it stable? No, not stable at all, because carbon's only got 6 electrons around it. Does carbon have a charge? No, it's neutral now, right? Because 4 valence minus 2 lines minus 2 dots is 0 charge, but only 6 electrons on carbon, so it's very reactive. So what happens now is the carbene reacts with the alkene. So we're going to take the 2 electrons on carbon, make a bond to carbon, and take the pi electrons and make a bond to carbon. And then that's your product. So you make a cyclopropane in this in this reaction. You know, so in general, cyclopropanes are not very stable, well, right, because of a lot of angle strain, so they're difficult to make. So that will be one reason why this is an important reaction in organic chemistry, because it's a way to make cyclopropanes. And there are ways to get rid of the 2 bromines or the 2 chlorines if you wanted to. Okay, so just as another example, I don't think I have that. No. So if you took that and reacted it with CHCl3 with potassium tert-butoxide, so then again, it helps in organic chemistry if you just learn to recognize reagents and what they're going to do. So if you see that, you know you're going to make a cyclopropane out of the alkene, and the carbon's going to be left with 2 of the halogens. So that would be the cyclopropane that you make. But of course, you do want to know the mechanism of how that reaction happens. Okay, so this is another way to make a cyclopropane. So it's another cyclopropanation reaction. So this is your reagent, CH2I2, and then if you react it with the zinc copper amalgam. So what basically is going to happen here is the zinc is going to insert between a carbon iodine bond. And you're going to make this reagent. So it's an example of an organometallic reagent. So you have an organic piece of the molecule attached to a metal. And so organic chemistry, there are lots and lots of examples of organometallic reagents that react with organic compounds to make a variety of different molecules. So this is an absolutely huge part of organic chemistry. So this is just one example of an organometallic reaction. Okay, so what happens now is this reagent that you just made is going to react with the alkene. So we're going to take the 2 electrons in the pi bond and we're going to make a bond to carbon, and that's going to kick off an iodine. And then we're going to take the 2 electrons in the carbon zinc bond, and we're going to take those and make a bond to carbon. So zinc is losing those electrons are remaining with carbon to make a bond to carbon. So now we have a cyclopropane, so we lost an I minus because an iodine left on the left, and then we lost a zinc iodide on the right, but zinc lost those electrons, so it's positive. So then we're going to make a zinc iodide side product. But the main thing we're interested in is the organic product, so you make a cyclopropane out of the alkene. Okay, so anytime you see this reagent, and that will be the only time you see this reagent in organic chemistry, in organic 1 or organic 2, you should just recognize that's how you make cyclopropanes. Oh, okay, so there's that reaction. We just did this earlier. So CHCO3 or CHBr3 and potassium tert-butoxide makes a cyclopropane, but you get 2 halogens left behind. Or if you use the Simmons-Smith reagent, then you would just make the cyclopropane without the 2 halogens, right? So because that CH2 basically is used to make a cyclopropane out of the double bond. Okay, and then lastly, the reactions of alkenes that we're looking at is alkenes are heavily utilized in industry to make polymers. So this will be one example. So basically you have an initiator. So in this case, it's going to be free radical mechanism. Could simply be just H+, just an acid, or just a base and an alkene, and to get a free radical, to get a polymerization reaction going. So the way that this particular reaction works, so the peroxide bond is very weak, so you're going to make 2 peroxyl radicals, and then that's going to react with the alkene. So we're going to take the 1 electron and take 1 electrons from the double bond to make a bond from oxygen and carbon, and then the other electron is going to stay behind on carbon. And so now you have an alkyl radical, and if you don't give it to anything to react with, then it will react with itself. So this is going to react with another alkene. So we'll take that 1 electron, take 1 electron in the pi bond, make a bond from carbon to carbon, and then the other electron stays behind on carbon. So now you have this alkyl radical, and it can react with another molecule of itself. So that can react with the CH2, make a bond between CH and CH2, and then the other electron in the pi bond becomes another free radical. So now you have this, and it can react with another molecule of itself. So basically in polymerization reactions, after you get it going, after the very first step with the alkene, then it just keeps reacting with itself over and over and over again. Okay, so if this happens, you make this bond, now you get the free radical there. Now you have this alkyl radical, and then it can react with itself again. So it can keep doing that several hundred or thousands of times. And so the very end of the polymer is different, but everything after that is just repeating units. And so there can be hundreds to thousands of these repeating units. And so the way to sketch the polymer, so we're just going to take the unit that's repeating. So this unit is repeating, right? So we're just going to break that out, and we're going to indicate it like that. That's the repeating unit. Well, that's the repeating unit. And to indicate that it's repeating, we're going to put that in parentheses with a subscript n. And n can be hundreds to thousands. So that would be the polymer. Okay, so this molecule is called styrene. Oops. And so this polymer is called polystyrene. So poly meaning, of course, there's many of them. So polystyrene is probably something you're all familiar with. Where do you find polystyrene used at? Right, that's what's in styrofoam. So that's what's used to package electronics in, for example, or a styrofoam cup if you drink coffee. Okay, so predicting the product of a polymerization reaction is easy, right? You just take that. Let's do this. So we're just going to take that and we're going to get rid of the double bond. And we're going to draw a line here, and we're going to draw a line here, and we're going to say that's going to repeat several hundred or thousand times would be the polymer. So if we did the same thing here, so if we took this alkene, and then what's going to happen in the reaction is we're going to get rid of the double bond, and then these carbons are going to just start repeating itself, and that would be the polymer. So this polymer, where you have CF2 units repeating, is what's called Teflon. So where's Teflon used at? So that's what you find used in non-stick cooking ware, skillet, for example, because this Teflon, nothing likes to stick to it, basically. Water doesn't like it. When you cook things, they don't like Teflon, so it just makes a nice barrier to your surface so that things don't stick to the metal surface. Okay, same thing if this is your alkene. So that's called vinyl chloride. So the polymer would be that, right? Which would be polyvinyl chloride, or PVC. So where do you see PVC used at? That's used in plumbing, PVC pipes. Okay, this alkene. So if you polymerize that, then just get rid of the double bond. And then we just have a bunch of those repeating units, right? So that's plexiglass. Okay, so this is acrylamide. So if you polymerize that, right, the amide. Why is that an amide? Because of that, right? That's an amide. So if you polymerize that, then you would make that. You would make polyacrylamide. So some of you biology majors may have heard of polyacrylamide before. That's used all the time in biology and biochemistry to make polyacrylamide gels. Okay, so you should be able to work backwards as well. So if you're given the polymer, what would be the monomer that it came from? So this is the polymer. And what it comes from is the monomer. So if you want to, the polymer is just going to have a double bond here, right? So that would be the monomer that polymer is made from. You can also have what are known as copolymers. So you can take two monomers and polymerize them together. So basically this carbon is going to end up attached to that carbon, and so you would get this polymer, you would get this copolymer. Right, this one's what's used to make saran wrap. Or in this case, if you took this molecule and that molecule and copolymerized them, so 1, 2, 3, 4. So 1, 2, 3, 4. So that would be those 4 carbons. And 1, 2, 1, 2. That would be those 2 carbons. So that polymer is what's called styrene butadiene rubber. That's what's used to make automobile tires. And as one last example, if we take these 2 molecules and polymerize them, and we can see that that is right here. And then this carbon structure is right there. So basically when these 2 polymerize, you lose a molecule of water. And so if you make this copolymer, this is a copolymer that's used in medicine. It's used in surgery. So this is what dissolving sutures is made from. So that can be used to make a thread that you can use to suture wounds with. Okay, so anyway, that's it for alkene reactions. So lots of reactions to remember, lots of reactions to stick in your head, so that you can do synthesis, for example. So let's just take one synthesis problem to end with. So let's say you had this molecule and you wanted to make this molecule. And so as long as you use this somewhere in the synthesis, you can use whatever other reagents you want in order to make the product. So I can just see the synthesis in my head because I've done organic chemistry long enough. So this is going to be 1, 2, 3, 4, 4-step synthesis. If you can't see the steps in your head, then what you might do is work backwards. So how could you have made that? So if you had this compound, then you could do an SN2 reaction. Right? You could take that and react it with NaCN minus. And then CN would attack here and kick off the bromine and an SN2. So if you had this, then you could have made the final product. Okay, so you always have to ask yourself, can you go from the starting material to the product in one step? And the answer is no. We have not looked at any reaction that would put a CN on a CH3, right? We have looked at a reaction that would put a CN on a carbon that's got a leaving group on it. So if there was a leaving group there, we could have put the CN on that group. Okay, have we seen any reaction that would take the starting material and put a bromine there? And the answer is no, we have not. Because if you take this starting material and put a bromine on, it would want to go there, tertiary, right? So we could have done this. So we could have put the bromine there, but how are we going to get it on the other carbon? And that's through a sequence of 2 reactions. So we could have made this compound if we had that alkene, right? If we had that alkene, we could add H and Br to those 2 carbons. So if you wanted to add H and Br to those 2 carbons, so this chapter 8 is looked at reactions of alkenes. So is that Markovnikov or anti-Markovnikov? Well, this carbon has 0 hydrogens and this carbon has 2 hydrogens. So if you want to put the hydrogen on the carbon with the least number of hydrogens, that's anti-Markovnikov. So what's your recipe for doing an anti-Markovnikov addition of HBr? It would be to use HBr and H2O2. Right, that would do an anti-Markovnikov addition. Put H on the carbon with the least number of hydrogens and bromine on the carbon with the most number of hydrogens. So if you had this alkene, you could make that. And if you have that, then you can make this, right, using different reagents. Okay, well, where did this alkene come from? So if we had this alkyl halide, we could make this alkene, right? So what's your reagents to take an alkyl halide and make an alkene? Well, that would be an elimination. It'd be E2 or E1, but only one is going to work. Because if you did E1, then it will put the double bond in the wrong spot, right? Because it always makes the most substituted alkene. So you need to do E2, and you need to make the least substituted alkene, which means you need to have a bulky base. Right, so if we had this tertiary alkyl halide, we can make this least substituted alkene. So there's your synthesis. So you would start with methyl cyclohexane, and you would do a free radical bromination to make 1 bromo, 1 methyl cyclohexane, and then you would do an E2 elimination. So let's throw some heat in there to make the alkene, and then you would do anti-Markovnikov addition of HBr, and then you would do an SN2 reaction, and you would have the products. You would have to do a sequence of 4 reactions to get to the product. Okay, so synthesis becomes a lot harder, right? The more reactions that you know, because the more possibilities there are. But that also allows you to make more complex molecules. And so, right, so this is one of the big parts of organic chemistry, is just discovering new reactions so that you can make more complex molecules or do things that you might not be able to do otherwise if it wasn't for all of these different reactions. Okay, we'll stop there.